In this video, we're going to look at special types of rings. So the very first thing that I want to do is I want to go back over what the definition of a ring itself is. We say that R under its plus and times is a ring if it satisfies all the ring axioms. And the ring axioms are, first of all, plus and times are closed on the set R. Second of all, we need that plus and times are both associative on the set R. The third thing is that we do need to have plus is commutative on R. The fourth thing is, which is a property that I have often put last in the past, but I want to go ahead and get it out of the way here. Times distributes over multiplication, meaning that if I have A times B plus C, that's the same thing as AB plus AC. Technically, there are parentheses around these guys, but multiplication is assumed to take precedence over addition inside any ring, and so we often will write that without the extra parentheses. The fifth property is that R has an additive identity element. And this identity element is usually called 0 sub R. It's the 0 element. And the sixth thing is that for every element, so all elements of R have additive inverses. And we've been through this in the past as far as what each one of these particular properties means. But in the rings that we've looked at, many of them have additional properties beyond these basic 6 ring axioms. And so what I want to do is I want to kind of collect our various examples and their extra properties and start looking at a basic hierarchy of special types of rings. So the very first thing that we want to do is we want to look at commutative rings. And in a commutative ring, the additional property is that times is also commutative. In other words, that we can now say A times B is equal to B times A for all elements inside our ring. And commutative rings have been an important set of examples that we've been looking at off and on throughout our study of rings. The next kind of special ring that we have studied in some detail are rings with identity. And we usually shorten this in handwriting to rings with a 1. And rings with identity, the additional property that they have is that there exists a 1 inside the ring with the property that A times 1 is equal to 1 times A, and both of these are equal to A for every element inside the ring. In other words, R has a multiplicative identity element. The third type of basic ring that we have looked at in our past several videos has been the idea of a domain. And the additional property in a domain is that there are no 0 divisors. Now, having no 0 divisors gives rise to two important ideas. Because we have no zero divisors, the first thing is that we do have cancellation laws. In other words, if A times B is equal to A times C, and we know that A is not the zero element, we can conclude that B is equal to C. Informally, what this means is that we can cancel the A's to go from this particular equation to that particular equation. We also have, this is the left cancellation law, we also have a right cancellation law, and the right cancellation law would be if BA is equal to CA, and A is not equal to 0, then we can conclude that B is equal to C. In this case, we're canceling the two A's on that side. It is important to remember that we do not have a double-sided cancellation law in general. In other words, if I know that AB is equal to CA, and I know that that A is not equal to 0, we can't immediately conclude that B is equal to C, and we can't conclude this because we do not know that A times C and C times A are the same thing. In other words, in general, A times C and C times A are not the same thing. The other thing that we know about domains is that we also have the important property that mimics real arithmetic, which is that if A times B is equal to 0, then in a domain we are allowed to conclude that either A is equal to 0 or B is equal to 0, or of course both of them could be equal to 0. And all of these zeros are the 0 in the ring, so let me put zeros, let me put R underscripts there. What I want to notice now is that there are things like the rational numbers that go beyond simply having no zero divisors to having an additional property. So I now want to look at some new definitions of special types of rings. So let's see, our first type of special ring is going to be an example that's going to be multiplied, that is going to be motivated by z. So I want to think about z under its plus and times. Z under its plus and times is a commutative ring. It is also a ring with a multiplicative identity, and it has no zero divisors. In other words, Z, with its usual arithmetic, is a commutative domain with a multiplicative identity. Now, these particular things are fairly important in a large number of areas of abstract algebra as well as linear algebra and other areas of mathematics, so it is customary to give these guys a name. And we're going to say any ring, so we call any commutative domain with a multiplicative identity an integral domain. So what this means is that when we say that I with a plus and a times is an integral domain, that means we know the following things. We know, first of all, that I is a full-fledged ring, so it has all of the properties of rings. We second of all know that times is commutative. The third thing that we know is that I does have a multiplicative identity, so I has a multiplicative identity element that we will typically call 1 sub I that lives in I. And the fourth thing that we know is that I has no zero divisors. And because I has no zero divisors, we know that I has cancellation laws. And finally, we also know that I has the property that A times B is equal to 0 implies A is equal to 0 or B is equal to 0. These are all equivalent to each other, and they are all because I is a domain and has no zero divisors. The next kind of special ring that we're going to be looking at is going to focus in on multiplicative inverses. So what we're going to do now is we're going to look at something called a division ring. And I'm going to say a set D with a plus and a times is a division ring if D is a ring with an identity that has the additional property that all non-zero elements of D have a multiplicative inverse inside D. In other words, for every little a inside D, there exists an A inverse also living inside D, such that A times A inverse is equal to A inverse times A, and these are both going to be the 1 in D. Now, it's important to realize something about domains. There are two things that I want to point out. The very first one is a major negative note. When we talk about domains, we do not require that times is commutative. And so it's very important to remember that if all we know is something is a domain, we cannot assume that A times B is equal to B times A. So in other words, we have to be thinking about A times B is quite likely not the same as B times A for at least some elements of D. The second thing that I want to talk about with domains is actually a positive thing, and that focuses on this part of the definition right here. Since every non-zero element of D has a multiplicative inverse, we know that all of those non-zero elements of D are actually going to be units. So, oops. But also note, every non-zero element of D has a multiplicative inverse is saying the same thing as every non-zero element of D is a unit in D. And in the last video, we found out a very important fact about units. This will imply that every non-zero element of D is not a zero divisor. Because we know that if you're a unit, you cannot be a zero divisor. And if every non-zero element of D is not a zero divisor, that says D has no zero divisors. And that says D is a domain. So every division ring is going to be a domain. So every division ring, let's see, that's not real readable. Every division ring is a domain. There are domains that are not division rings. The set of integers is the canonical example. But if something is a division ring, then it will be a domain. Now, the final special type of ring that we're going to define is going to be a commutative division ring. So let's look at a commutative division ring. A commutative division ring is called a field. And fields are things that you have studied in the past. Some basic examples of fields that you know already and that you have lots of knowledge about are the rational numbers under addition and multiplication, the real numbers under addition and multiplication, and the complex numbers under addition and multiplication. They are all examples of fields. And so when you hear something is a field, you should be thinking at least somewhat in terms of their arithmetic behaves sort of like the arithmetic in Q, R, and C. So I want to again stress, what does it mean? So when we say F under a plus and a times is a field, we mean, and so we know all of the following things are true. First of all, F is a ring. So all of the ring axioms apply. And everything else that we know about rings will apply to fields. The second thing is that we know that times is commutative. In other words, this field is going to be a commutative ring. The third thing we know is that times has a multiplicative identity element. In other words, the field contains a multiplicative identity element. Usually we write it as 1 sub F. So F is also a ring with identity. The fourth thing is that F is a division ring. And what that means is that we know every non-zero element has a multiplicative inverse. So if A is inside F and A is not equal to 0, there exists an A inverse inside F such that A times A inverse is equal to A inverse times A, and they're both going to be equal to the 1 inside the field. But being a division ring also implies a few other properties that are important. We also know that we have the ability to say that there are no zero divisors. And we also know that if A times B is equal to the 0 inside the field, then either A is equal to the 0 or B is equal to the 0. And when you look at this long list of properties, this is exactly what you wind up having under the traditional definition of a field inside of a course like linear algebra or even high school algebra. It's just that a significant number of the properties are buried in the fact that F is a ring. Well, we have had a lot of definitions, and what I want to do is take the time to organize all of these definitions into what is tantamount to a hierarchy of special types of rings. So I'm going to start my hierarchy with plain old ordinary garden variety rings. They are the most general of our structures. Now, as we add properties to that basic definition, we get different kinds of special rings, but they all stay as rings. Well, the first thing that we might have is we might have a commutative ring. And in a commutative ring, star is commutative. That's the only additional property over the ring axioms. Well, we might also have rings with 1. The additional property is that we have a multiplicative identity element. And then we've also seen that we have a special type of ring called a domain, where the special additional property here are no zero divisors. Now, it is important to remember that no zero divisors buys us several important facts. It says, among other things, that we have cancellation laws, and we also have a times b is equal to 0 implies a is equal to 0 or b is equal to 0. And again, these are inside the ring. So it's important to realize that all of these facts are built into saying that there are no zero divisors. But we also have some other special things that we've looked at. Integral domains are commutative rings because their multiplication is commutative. Integral domains have to have an identity element, and so they are a ring with a 1, and integral domains are also an example of domains because they have no zero divisors. So an integral domain is a special type of each one of these special types of rings. Then we had the division rings. Now, the division rings had to have an identity element, and it turned out that they were domains, but they also had one additional property. They had an additional property that if A is not equal to 0, then A inverse exists. In other words, everybody had a multiplicative identity. So division rings sit over there. And then the final special kind of ring that we had was something that was nothing more than a commutative division ring, which meant that it actually is an integral domain. And these were our fields. With a field, what we have is we know that we're a division ring. We know that we also have an identity because we are a division ring, and we have multiplication is commutative. And because we're a division ring, we also know that we're a domain. And since we have all three of these properties satisfied, we also have to be an integral domain. And it's important to understand that this particular schematic diagram has not only the ability to help comprehend the special definitions for each of these special types of rings, but it also says something really important about the basic idea. Anything that you know about a ring is going to apply to every single one of these other structures. And anything that you know about a commutative ring is going to apply to both integral domains and fields. And anything that we can prove about rings with identity will apply to integral domains and division rings. And anything that we can, and because it'll apply to both integral domains and division rings, it'll also apply to fields. Anything that we can prove about a domain will apply to domains and division rings and fields. And anything that we know about integral domains will apply to fields. And anything that we know about division rings will also apply to fields. So this will also tell us which theorems will apply to which kinds of structures. So any theorem that starts off with the hypothesis, if something is a ring, will apply to every single one of these specialized algebraic structures.